so we looked at limits going to infinity and negative infinity on Friday. Today, we're going to look at limits that are infinity or negative infinity. So essentially, we're going to be looking at vertical asymptotes. So we previously looked at the horizontal. Now we're going to look at the vertical. With vertical asymptotes, we often speak about end behavior. So end behavior is what is a function doing as it goes out infinitely. So we're also going to talk about the end behavior model in calculus. So a vertical asymptote is a line x equals a on a graph such that the limit as x approaches a from the left is positive or negative infinity, and the limit as x approaches a from the right is positive or negative infinity. So if your graph contains a vertical asymptote, then it will automatically go to an infinity. So if a graph has a vertical asymptote, it will automatically go to an infinity. However, because infinity is not a set value, this is where we also kind of write like it goes to plus or minus infinity / does not exist, because it's not approaching a number, so it doesn't necessarily exist.
Katie Goodrock, Austin Willer, Nick Conley, Maria Formanek, Anna Bliss, Jason Smith, Dominic Spino, Lucas Strimmel, Noah Vensko. Those students, please report to the office.
Second period is almost over. To find out if a function has a vertical asymptote, we need to determine where the function is undefined. So to find the vertical asymptote, we find where it's undefined. To do this, we set the denominator equal to 0. Graphs have vertical asymptotes and infinite limits. They go hand in hand. Why? Because they're increasing or decreasing without bound. So what are the vertical asymptotes of f of x equals 2x over the quantity x minus 3? So what we would do is the first thing is to find the vertical asymptote. So the first thing you want to do is find your vertical asymptote. So the vertical asymptote occurs when x minus 3 equals 0, which means I have a vertical asymptote at x equals 3. So once I've identified my vertical asymptote, so once you know the vertical asymptote is at 3, now you want to find the limit to the left and to the right, but we don't have a calculator. So you need to be able to determine the limit from the left and the right based off something relatively close to 3. So if we're looking at 3 on the plus side, that's 3 to the right. So something near 3 to the right, but not the number 3, because if you plug the number 3 in, you get 6 over 0. So let's plug in or use 3.1. So if I were to plug 3.1 into this function, 2 times 3.1 is going to be positive. 3.1 minus 3 is going to be positive. So a positive over a positive tells me that the limit as x approaches 3 from the right is positive infinity. To the left would be like plugging in 2.9. So 2.9 times 2 is positive. 2.9 minus 3 is negative. A positive over a negative tells me that this is approaching negative infinity. So the behavior to the left or the right of the vertical function is as follows. So you would be able to graph this and say at 3, it's going to negative infinity on this side and positive infinity on that side. We also now know that because this is x and this is x, at x equals 2, there's a vertical asymptote. So my graph, we could almost get a rough idea with the vertical asymptote at 3, the horizontal asymptote at 2, roughly what that graph looks like. You also now can more easily describe domain and range. Because the left-hand limit does not equal the right-hand limit, the limit as x approaches 3 does not exist. Okay, what are the vertical asymptotes of 1 over x squared? Describe the behavior to the left, to the right, etc. So once again, x squared equals 0. Thus, vertical asymptote at x equals 0. Behavior to the left and to the right says that we would plug in 0.1. So 1 over 0.1 squared is positive because anything squared is positive. So this is positive infinity. Negative 0.1 squared is still positive. So this is positive infinity. Because the values of the function approach infinity on either side, we can say that the limit as x approaches 0 of 1 over x squared is infinity slash dne. Because it's still not a numerical value, so it really does not exist. However, we could tell that they're both going to infinity. And again, horizontal asymptote at 0, because the denominator is greater than the numerator. And again, it should make sense that you can never get a negative number with a positive on top and a positive on bottom, always. So domain is all reals except 0. Range is 0 to infinity, not including 0. Tangent. Looking at just tangent by itself right now, is there an obvious denominator? No. But we know that the tangent function 100% has vertical asymptotes. Why? Well, that's because the tangent of x isn't really tan. The tangent of x is really sine over cosine, and cosine 100% equals 0. So everywhere the cosine of x is equal to 0 will act as a vertical asymptote on tangent. So these are the ones you don't like, because these are the ones where I add my plus or minus k's with pi's, because they repeat over and over and over again. So the cosine of x equals 0 when x on the unit circle is equal to pi halves, and on the unit circle when it's equal to 3 pi halves. What that means in reality is that the cosine of x is equal to 0 at pi halves plus we actually only need pi k, because we don't need to put it with the 3 pi halves, because if you add pi to that, like pi k, you would hit the bottom, then hit the top, then hit the bottom, then hit the top, because it happens every half of a circle, which is pi. And then the last part to that would be that k is an integer, because it cannot be a fraction. It has to be an integer.
I understand this one with the vertical and horizontal.
So the limit as x approaches pi halves from the right of sine or tan over cosine. So again, think of the unit circle. So if you're coming from the right to the right of pi halves is actually like the opposite in the unit circle, because the unit circle's counterclockwise. So if you're coming at it from the right, you're coming from quadrant 2. So in quadrant 2, sine is positive, but cosine is negative. So from the right, we got negative infinity, because you would have a positive over a negative. And then the limit as x approaches pi halves from the left now is coming from quad 1. Everything in that quadrant is positive, therefore it's positive. So it's kind of like goofy, because if this is your pi halves, to the right is at the negative, and from the left is at the positive. So we know that this repeats every pi halves. So then it really is how you get your tangent graph. It repeats infinitely over and over and over again.
So for our answer, do we need to have the cosine x equals 0, the x equals pi halves? Is like all of that part of one answer?
That is the vertical asymptote question, yes.
Okay.
So like this would be like where it says like describe the behavior to the left and right is here. When it says to find the vertical asymptote, sorry, it's right here. I was reading the word tangent. So like those are the two parts to the question. Does that make more sense? I think end behavior is pretty easy because it connects back to horizontal asymptotes, which you said you don't like so much. So hopefully this will help. So the end behavior is really saying, all right, I want to take the highest power of the top, the highest power of the bottom, and I want to compare them to really tell me how this function is behaving without all the other parts of the polynomial function that go with it. So what you really do is you take these crazy functions and you simplify them down to a singular function on top, a singular function on bottom, just to determine how it behaves at the end. So this, again, kind of works to the slant asymptote, because we know how they behave at the end if the coefficients are the same. We know how they behave at the end if the bottom is greater than the top. But where we struggle is when the top is greater than the bottom. So this kind of helps create that connection. So if a function provides a left and right end behavior model, we just call it its end behavior model. I shorten it to EBM because I don't like writing out long words. So end behavior model is EBM. So the end behavior goes to infinity and negative infinity. So again, it brings back that connection of the horizontal asymptotes. So it might not ask you for the horizontal asymptotes, it might describe it as end behavior models. So what we want to do is compare these crazy functions, f and g. So f is a polynomial, g is a polynomial, their coefficients are the same, their highest powered exponents are the same. If we put them in our calculators, at first they'd behave differently, but as you zoom out and zoom out and zoom out and zoom out, what we would see is that they look identical. So zoomed in on a window -10 to 10, you'd see both graphs. Zoomed out on a window -1000 to 1000, you'd see one graph, because they would sit on top of each other once you get really, really big. And that's really what we want to talk about, is how do functions behave as they get really, really big? Well, they behave like their highest powered function. That's really the goal of end behavior, is how does a function behave as it gets really big? Well, it behaves like its highest powered piece of the function. So here we have 2x to the 5th over 3x squared. So it's not a slant asymptote because the degrees are more than 1. It's not a 0 because the degrees aren't the same. Or it's not a 0 because the bottom isn't greater than the top. And it's not the coefficient because the degrees aren't the same. So what we want to do is construct an end behavior model. And the end behavior model is simply taking the highest powered from the top and the highest powered from the bottom and comparing them. So the end behavior model for f of x is 2x to the 5th over 3x squared which simplifies x to the fifth over x squared to 2x cubed over 3. So 2x cubed is an odd function. So odd functions start low and go high. They also end in opposite directions. So odd functions end in opposite directions, and an positive one starts low and gets high. So this is a cubic model. So what that means is that the limit as x approaches negative infinity for f of x, and the limit as x approaches positive infinity for f of x will be the same. Remember, f of x is way up here, as the behavior of 2x cubed over 3. So however this function behaves as it's really, really big is how this function will also behave as it's really, really, really big. So that's an odd function. So negative infinity is negative infinity. Positive infinity is positive infinity. Does that make sense though? Does that help with like the end behavior and like what they're doing? So what I'm going to do is I actually have a chart I give my Algebra 2 kiddos when we do end behavior for polynomials. I'll send it to you because it has like the even, the odd, and like how they behave if they have a positive or a negative coefficient. It's like in my files in chapter 6. So I will send it to you. Once again, now we have g of x. So you look for the highest power to the top, highest power to the model and the bottom, and create your end behavior model. So the end behavior model for g of x is 2x cubed over 5x cubed. Well, now x cubed over x cubed go away. So what that means is this behaves like y equals 2/3. That should still make sense to us, because if I asked you to find the horizontal asymptote for g of x, you would have told me 2/3, because the coefficient at the top and the bottom are the same. So what that means is that the limit as x goes to negative infinity of g of x is 2/3, and the limit as x goes to infinity of g of x is 2/3, because this graph is going to have a horizontal asymptote at 2/3. So as it gets really, really big or really, really small, it's approaching 2/3. Oh, yeah, sorry. Clearly, I can't.
See, I wrote down 2/3 at first too, because I looked at the first one.
And then my problem is, like, sometimes when I look at like the board, because it's the handwriting is so much bigger than like my real handwriting, I swear like everything just gets blurry on my head. Like if I took my notes and like did it on a document camera, I get them right more than when I do them on the board. I just think sometimes on the board I make like,
It's the pressure.
no, it's not the pressure. I literally feel like I just can't like see the whole problem. Like it's so zoomed in because I'm so close to it. Like it's just really zoomed in for me. I wish I could write like on a tablet so I could write small and then it just still appeared big for you. Like when I used to do my problems on the iPad. But that was so, like, that's so delayed. I stopped doing it. I mean, we can't do calc without exponentials, because exponentials just occur so naturally in the real world. They're such an important concept to really understand. And I feel like the graphs of e to the x and ln of x are graphs we haven't fully always conceptually like understood them. So if something is growing, e to the x starts small and gets big. So e to the x is the blue function up on the screen. So as e to the x is getting bigger, it's growing. e to the negative x would be decay because the power is negative. So it's the lime green function. So as e to the negative x is getting big, it's getting small. So again, think about when you're sick. When you're sick, you have a lot of bacteria in your system. And then as you get better, if you're taking antibiotics especially, it's like, whew, you feel so good so quickly because the antibiotics did their thing. But you take antibiotics for 10 days because that virus is still there. And it's lingering, getting closer and closer to not existing at all. So that's why actually people that get like strep throat over and over again, it's because once you have it and it's in your system, it is always in your system because it can never actually go back to zero. So that's why like people have their tonsils removed because once they get it, some of them never lose it and then they get it worse and worse and worse every time until they get it so badly they have to have their tonsils removed. Fun little health fact. So how do exponential functions behave? Well, they behave exactly like we described in that model. What happens if you add or subtract an x value to them? Well, it just kind of changes the end behavior a little bit. So now you have to look at the behavior of each one. So we have g of x is equal to x, and that's the right behavior model for f, while h of x equals negative e to the negative x is the left end behavior model. So what that means is really that if we were looking at the limit as x approaches negative infinity versus the limit as x approaches positive infinity, the end behavior model for x plus 1 over e to the x is as follows. So what you want to do is almost look at them separately. So we know that x is going to start low and get high. And we know that e to the x is going to start high and get low or approach zero. So if you combine them, what they're saying here is that the left end behavior model for f of x is going to come from that e to the negative x, whereas the right end behavior model is going to come from x. So left end behavior is going to be at negative infinity. So you have to get, honestly what I do is get a common denominator since e to the x is down below. So what I would do is say, okay, let's get a common denominator. So I'm going to multiply x times e to the x. So you have e to the x times x plus 1 all over e to the x. So the highest powered exponent is x e to the x. And the bottom it's e to the x. So this is like x e to the x over e to the x. So this is how my function is going to behave. So if we go to negative infinity, x being negative infinity means it's going to be negative. E to the x, where e is at negative infinity, would kind of drop it to the bottom. E to the x would bring it to the top. So therefore, this function is going to go to negative infinity because it's kind of like e to the x over e to the x is kind of like 1. So it's really going to behave for that. And then positive infinity. So e to the positive infinity and e to the x over positive infinity is going to push my graph to positive infinity. Absolute values. Absolute values are piecewise functions by definition. So So an absolute value is a piecewise function by definition. So if you just looked at that and you applied substitution, you get 0. Because absolute value of 0 is 0. Well, let's look at it separately though. The limit as x approaches 0 from the left, first the limit as x approaches 0 from the right, knowing that the absolute value of x is really negative x and positive x for x less than or equal to 0 and x greater than 0. So that should still make sense to us that if we plugged into the left side of the piecewise versus plugging into the right side of the piecewise, I'm still going to get my zeros. Where it becomes more important is once we put absolute values into fractions with other functions. So right now, the end behavior for absolute value of x, we also could know end behavior. Absolute value of x is a v, so both sides are, So the left and right end behavior is at infinity. So now, why does the limit as x approaches 0 of absolute value of x over x not exist, where the absolute value of x was 0? How does that denominator change it? So again, creating that piecewise function from this, what does that make your piecewise function? Well, it makes it negative x over x versus positive x over x. So negative x over x is -1. Positive x over x is 1. So now, if you look at the limit as x approaches infinity, the limit as x approaches 0 from the left versus the limit as x approaches 0 from the right. Well, from the left, the absolute values are really not there, so it's -1. Or even if they were there, if you plugged in like -0.0001 over -0.0001 to like predict it, since you can't plug in 0, a positive over a negative is a negative. And here, if you plug in positives on top and bottom, man, I'm glad I got his charger when I did. You would get a positive, so a negative equaling a positive 1, They're not the same, therefore the limit does not exist. Make sense? What type of function is this? Or what theorem? Sandwich. Yeah, should have gone that way. This way. Sandwich or squeeze. So what do we predict it's going to be? 0. Why do we know it's going to be 0? Because the limit as x approaches 0 to negative x squared is 0. The limit as x approaches 0 of positive x squared is 0. And because x squared is less than or equal to x squared sine 1 over x, less than or equal to x squared. Therefore, the limit as x approaches 0 of x squared sine 1 over x is 0 by the sandwich or squeeze theorem.
Mine's been in my
They
locker.
just pushed them over there. Well, that's what I said. Like, we had one over here, so you could have one at home and one here.
I just take pictures of
Mine's
it.
never left my locker.